I wanted to look with you at the calendar, just so that you are kind of aware of where we are. So today is the 12th of the 12th month. It's 12, 12, 18 today. If you hadn't known that, it's kind of fun. We are going to work on some more impulse momentum problems. We're going to go over homework. We'll spend some time doing some things. I'm also going to introduce to you the egg drop stuff. You do have homework for tomorrow, okay? There are a couple of problems, and then there are a couple of kind of conceptual questions. The answers to the problems are on Canvas, and they're also on my OneNote, so you'll see them in the video as well. Tomorrow, we're going to have a short impulse momentum quiz, just to make sure you're feeling good about it, make sure that you know how to solve those problems. They will not involve kinematics material. It will just be impulse momentum. So unlike, I think it was question 2 that you did for homework today, which we'll go through because I think it's important and it's interesting, but it won't be questions like that. It'll be like 3, 4, and then the ones for tonight as well. So we'll do that. On Friday, we'll be getting ready for our egg drop, and then on Monday, we're going to actually drop some eggs, and then Tuesday of next week, we will take our test over Unit 4, okay? Again, I want to get that done early in the week so that if there are people that feel like they would like to do retakes, there's an opportunity to do that before winter break, because I don't want that to be a stressor over the break for you. Questions on that so far? Okay. So my plan today was to go over homework. As I said, I've got a couple of other questions to work on, and then if we have time at the end, we'll just kind of work on homework. Just as much practice as we can get to today is best. So you're going to drive this conversation to start. The homework 195, 3 and 4, and 197, number 2. Any of those 3 or all of those 3 or some combination that you would like to go over? And if the answer is no, that's totally fine too. They go okay. 195, number 3? Yeah. For sure. Page 195, number 3. All right, so if you don't have a textbook out in front of you, I would encourage you to get one just so that you can follow along. You know what the problems are going to look like, that sort of thing. Again, the quiz tomorrow, I would expect to look a lot like these kind of problems. I'm not intending to throw anything else scary at you. The things that you're going to need to know are that F delta T is equal to M delta V. Okay, so that the impulse is equal to the change in momentum. That's going to be your big key thing there. I don't expect this will be a long quiz, just a couple of questions to make sure that we're feeling good. All right, 195 number 3 says, a 0.4 kilogram soccer ball approaches a player horizontally with a velocity of 18 meters per second to the north. The player strikes the ball and causes it to move in the opposite direction with a velocity of 22 meters per second. What was the impulse delivered to the ball by the player? How are we going to start this problem? How do we start every problem? We'll write down our givens, aren't we? So you're looking at the problem too. Tell me what's something you know.
Soccer ball has a mass of
0.40 kilograms. Excellent. What else do we know? Yeah.
Soccer ball's initial velocity is 18 meters per second.
18 meters per second. Awesome. And it says that that's to the, north? Just so that we're kind of paying attention to that. Put that in parentheses, just, oh, by the way. What else do we know? Anything? Final velocity is 22 meters per second. How does the direction of the final velocity compare to the direction of the initial velocity? It's negative. So it's opposite direction, right? So you can call either one negative, but since we called VI positive, we'll go ahead and call the final velocity negative for sure. Any other things that we know in this problem? Is that it? And it asks, what are we trying to find? The impulse. How am I going to write that in my givens as a something equals question mark? F times T? Yep. And it feels kind of funny to do that. If you really wanted to have another letter, I think I told you guys that J is the letter that you can use, but it doesn't matter that much. But if you feel like F times T feels funny to write down, you could write down J, then
Is it just
Yep.
the lowercase?
A capital J.
Capital J?
Yep. Just like that. I like very rarely see it I mean, like some books use it, but not all of them. Yeah. All right. So how are we going to solve this problem? Okay. So we got VF minus VI because that's really just the change in velocity, right? We'll take that VF minus VI times the mass, and that will give us our impulse, right? F delta T. So it's just going to be 0.4 kilograms times, so final velocity is negative 22 meters per second minus 18 meters per second. So is the impulse going to be positive or negative? What's that? Negative. So it's 0.4 times 4, right? Negative 4. Is that right? Did I do that right? Yeah. So what do you get for the impulse then? Did I do something wrong? What'd I do?
I don't. You put the. Would it be just negative 22 minus 18?
Yeah, I just changed it to a plus and I add the opposite just because that's how I was doing that's how I was gonna do my, right? Negative 22 minus 18.
Oh, you said negative 4 times 0.4. Negative 40 times 0.4.
Did I say 40? I didn't mean to say 40. I'm sorry.
Well, no, you said 4.
Oh, but it should be 40. I see what you're saying. Yeah.
that's-
Sorry.
that's
Yeah.
what you're saying.
Sorry. I didn't mean to confuse you with my poor speech pattern today. Yeah. Negative 40 times 0.4 gives us negative 16 kilogram meters per second. The units of this are the same as the units of momentum, right? Because it's just a change in momentum. You could also write this as Newton seconds. That would be just as accurate. If it makes you happier to write it that way, by all means. Easy enough? Any other ones of the homework that you would like to go through? I'm going to pop back to the list just so you can take a look at it. Question number 4, do you want some answers? Maybe that would be helpful. Part A, the answer was 9 meters per second to the right. Part B was 15 meters per second to the left. And then from page 197, number 2, part A was 14 meters per second north. B was 42 meters north. And C was 8 seconds. So for question 2, it says a 2,500 kilogram car is slowed down uniformly from an initial velocity of 20 meters per second north by a 6,250 Newton braking force acting opposite the car's motion. Use the Impulse-Pmomentum theorem to answer the following questions. So the first one says, what is the car's velocity after 2.5 seconds? So in order to do this, I'm going to go ahead and jump back over here. Page 197, number 2B. So in part A, you found that the final velocity was 14 meters per second. Is there anybody that would like me to go through that part? Or are you okay with it? We okay? Okay. So in part A, you found the final velocity was 14. You also know that the initial velocity was 20. And you know that the time, so I'm actually going to change this to part B because we're actually doing part B. It says is 2.5 seconds. And they want to know how far does it go. So we're trying to find a D or an X. So we need to find an equation that has those 4 things in it. So this is the kinematics part. This is where we get out our equation sheets again. So if you have to dust yours off because it's been, hiding in your notebook for the last couple of months. Go ahead and pull that equation sheet out. See if you can find an equation that has displacement, time, initial and final velocity in it. Go ahead and pull that out. We're going to look at a couple things on there as well on your equation sheet. Okay? So final velocity, initial velocity, time, and displacement. Do you find that equation? Can you see it? Which equation am I going to use? We're looking at the top box, top left-hand corner, one of those bottom four equations in that box. Yeah, Ben, what you got?
Would it be delta S equals half df plus di delta t?
Mm-hmm. Nice job. We just plug it in, right? Half of 20 minus 14 times 2.5. Okay. Stella, does that make sense to you? Given you're the one asked, right? Yeah, I just want to make sure we're okay. Yep.
Oh, I didn't ask the question.
Oh. Somebody asked about B, right? Who was it? Oh, it was Leanne. Jeez. Leanne, does this make sense?
Yeah.
Yeah, okay, good. I just want to make sure. Okay. Anything else you want to go over? All right. All right. I would like for you all to turn then to page 218. We're going to look at one together. I pulled this one off of your homework, so you're going to do a couple of others from page 218 tonight, but I wanted to just look at question 5 together real quick. It's a conceptual question, but I want to make sure it makes sense to you because you know what? There'll probably be a conceptual question on your quiz as well because I want you to understand the impulse momentum theorem, not just mathematically, but also from a conceptual perspective. So we're looking at page 218, number 5. Okay. It says, anybody done gymnastics before? No. Anybody ever done a cartwheel before? Or a somersault or jumped? Anybody jumped before? Yeah, you've all jumped before at some point. It says gymnasts always perform on padded mats. It says use the Impulse-Pmomentum theorem to discuss how these mats protect the athletes. Talk to me. How would you answer that question if you had to do it, I don't know, on a test or something like that? Quiz.
Kind of bouncy.
They're kind of bouncy.
Yeah.
Absorbs the force.
Absorb, tell me what you mean.
Like it takes the impulsor, can withstand it and slow it down. It's not like a brick wall, but it's not like it's liquid. It's something that can slow it down and stop it.
Okay, so I'm going to write down what you said because so the padded mat, the feature of it, as opposed to a brick wall or a brick floor, is that it can do what?
Can absorb like the force without hurting whoever's falling.
Okay, so that is true. I want to know from a physics perspective why. Use physics to talk about it. Why don't you find a partner if you're not with a partner? I'm going to give you a minute to have that conversation. Think about it. Think about it from a physics perspective. F delta T equals M delta V. Think about those gymnasts you've watched. Think about somebody you've seen do a flip. Think about how a padded mat can help this out. I want you to talk about it. Go ahead and have that conversation. Go, go, go. So the gymnast does a big flip, right? And in doing a big flip, she's way up in the air. And she's going to fall down to the mat, right? What's the mat going to do? What does the floor do to anything as it comes down to it?
applies a force back.
It what?
It applies a force back.
For sure. Yeah. So any object is going to have a force. So the floor, whether it's padded or not, applies a force, right? Oh, I'm on free, so you can't see my terrible word force there. The floor applies a force, right, to the gymnast. What does that force do to her or him? What does the floor do to him? Stops him, right? So the technical terms, as the physicist that you are, you would say that the floor, if he stops them and they were moving before, what would we call that? What's that word? When you have one velocity, change it to another velocity. No, it accelerates them. Yeah, sure, it's going to accelerate them. Accelerates the gymnast. Does that change their momentum as well? Yeah, right. Changes the momentum. So, why a mat? Emma, what you guys talk about? Yeah.
Because like it pushes back a little bit. Like it's been a while since I've been on it.
It's okay.
What I'm thinking is like there's a bit of a spring in it.
Mhm.
So instead of just hitting a hard surface where it wouldn't absorb any of the force that they apply, it pushes back so that some of the impact goes into the floor and not just them.
Okay.
I don't know how to put that in.
Okay. No, you're fine. That was a good start. Like that's a good way to start it out. Question for you. Well, I think we said the floor applies a force to the gymnast. Y'all agree with that? Does the gymnast apply a force to the floor?
Yeah.
Which force is bigger?
It's the same.
It is the same, right? Absolutely, we know that. Third law says it has to be. So the forces are the same. And there's a change in momentum for sure. So the reason that I'm asking that is because a lot of people want to say this absorbs the force thing. I don't know what that means from a physics perspective. What does that mean to absorb the force? Can you tell me in physics words?
Just the same back at you. Doesn't take it away.
Transfer force.
What do you mean? I don't know what that means either.
You kind of like, never mind. I was going to say give your force something else, but then you would also still be putting the force on it.
Right. So think about punching a wall versus punching a pillow. Which one hurts more?
The wall.
Why?
Because it's hard.
Because there's no way, I mean, the wall that way.
Yeah, but
So what if like you have a friend that's holding a pillow, right? Or holding a piece of wood and you slam your fist into it. Which one's going to hurt more? The wood is, right? Your fist is moving fast. Your fist is going to stop. So your fist experiences a change in momentum, yes? Why does the pillow hurt less?
Because it absorbs more force.
What do you mean?
I don't know. Does it take more time to absorb?
It what?
Does it take more time to absorb the force?
Okay, that's where we need to go, right? If you think about slamming your fist into a pillow, does your fist stop at the front edge of the pillow? No, your fist gets to move through that whole cushy pillow, right? And so the force of the pillow, you're like, cushy pillow, what? Yeah, but as your fist moves, it's slowing down. But it slows down. It's the same change in velocity, but it slows down over a whole lot longer, what?
period of time.
Period of time. Are you with me there? So either way, if you're slamming your fist or if you're doing backflips and then you land, in either case, right, you're changing your momentum. And in either case, you have to apply a force. But if you have a longer time over which to change your momentum, what does that mean about the force that's acting? If the time goes up, you have the same change in momentum either way. What does that mean, guys? Let's do the math. Okay, here we go. Let's do the math. Let's say that we have a person who has a mass of, I don't know, we're going to say 43 kilograms. Get out your calculators if you don't have them out yet. We're going to say that the person is moving at a speed of, I don't know, 8 meters per second, and then is stopped. If that stopping happens really fast, like let's say, we're gonna have two examples here. A time of like 0.01 seconds. Tell me what the force that person is gonna feel is. Can you do that problem?
Yeah.
We just did that problem earlier, didn't we? Everybody do it. Everybody do it. Don't rely on the loud people. Don't rely on the people on the other side of the room. I want you to do it. Solve it for force. So F is going to be equal to M times V final minus V initial divided by the time. Big force? How big?
I got 34,000.
Yeah? Do you guys agree with him? I don't always agree with what Jordan says, so I want to make sure. Before negative because it's going the opposite direction of the direction they were moving. If instead, so this is like the brick wall, right? It's going to happen really fast. Hot diggity, we have to stop, right? Whereas if we have a force that's applied over, let's say, 0.1 seconds. You might be able to figure that out without a calculator, but if not, go ahead and plug it in. How big's the force? 3,400? Negative. As the time goes up, the force goes down. I want you to think right now with your table partner. I want you to think, see if you can come up with another example where you can use your knowledge of the impulse momentum theorem to increase safety or increase comfort or anything like that. Have a conversation. Go right now. Talk. We're going to share out. You guys want to go first? No? All right. You guys want to go first?
Sure.
Fantastic. What you got?
Airbags deploying in a car.
For sure, right? Airbags deploying in a car. Why?
So if like you have an airbag that is like say, I don't know, it says inside it's like 100 kilograms coming out at 10 meters per second, it's not going to feel as good when it's like 50 kilograms coming out at 40 meters per second.
Yeah. And honestly, when we're talking about airbags, like the airbag is the thing that's is giving you that space to slow down, right? I don't know if any of you have experienced an airbag before, but I hope that you haven't for your own sake, but hopefully you've maybe seen a video of one. When an airbag pops out, or let me back up. Without an airbag, if you're driving in a car, especially if you don't have a seatbelt on, if you get in an accident, you hit something, you're an object, and without a net force, there's no acceleration, right? Which means you're just going to keep going. But as soon as something applies a force to you, I don't know, like the dashboard, okay, or the windshield, or maybe you fly through that and you hit the pavement. In any of those cases, are any of those going to give you any give? And so your velocity, your change in velocity is going to happen, but the time through which that change in velocity happens is going to be very short. Whereas with the airbag, you got all of that space, right? It's like a big pillow. And so it's able to absorb, it's able to decrease that force by giving you more time to slow down. It's a good example. Now? Yes? No?
I guess.
Go ahead.
Well, one could be like, could you use water, like when you jump off of a high, like, not in a building, but like off a diving board, you go into water instead of hitting the tree.
Absolutely. I mean, absolutely. It's exactly the same concept, right? If you, oh my gosh, I can't even imagine, right? But if you jumped off of a high thing and you jumped and you hit the pavement, okay, again, change in momentum is the same. It does not matter. The change in momentum will be the same, but if you have water there, that water is going to slow you down at a much slower rate, right? And by slowing you down at a slower rate, the force is going to be much less, much more pleasant, right, than if you landed on concrete or, anything else really, right? Yeah. What else would you guys come up with?
We did the difference between punching a punching bag with and without gloves.
For sure. Why?
The gloves help slow down the impact.
Absolutely. It increases the time, doesn't it? Anytime you can increase the time, you decrease the force. Absolutely. Go. What'd you guys say?
We talked about the crumple zone of the car when you get into a car crash, and they try to make them better so that when you get into a car accident, you're not hurt.
Exactly. So it's the same concept as the airbag, except more like for the whole car, right? So like the car that my dad drove when he was, in college was this huge chunk of steel, right? Which had no crumple, like it would just boom, stop, right? And when it goes boom, stop, the time is very, very short, which means the force, if you would have gotten in an accident, would be very, very high. Whereas all of the cars that are manufactured now, they are able to withstand that change, right? And they literally, they crumple up. And by doing that, it increases the time, which decreases the force that you feel. Yeah. It's all about safety. Absolutely. Is this making sense? Okay. Fantastic. All right. Quick kind of related question, kind of a little bit not related question. The next thing on my list of things for us to do today. Oh my goodness. Okay. No, we're going to do this out of order because I want to make sure that we have time to do the egg drop stuff first, and then we'll do the bouncy balls if we have time. All right. So I mentioned that tomorrow you're going to quiz, and then on Friday, is that right? Because today's Wednesday, right? So tomorrow we'll quiz. Friday you will start to build, you will start to design your egg drop container. So some of you may have done, I'm going to hand this to you right now as you're walking by. You may have done something kind of like this before, maybe not. If you haven't, you have an opportunity today or this week. My egg drop challenge is a little bit different than some other teachers or some other programs, so I want to explain a few things to you about it. So I'm going to just kind of read through some things with you so that the instructions make sense. We will do a few different design challenges throughout the year. This is just happens to be the first one, so I need to share with you the kind of the expectations and what's going to happen here. So the goal, yeah.
I remember walking in the hallways and seeing.
Last year, yeah, we did this. Absolutely. Yeah, it's fun. It's good. So the goal for the challenge is to design and build a container that will provide an egg safe transport during impact to the ground, during an impact from the ground, off of a 5.3 meter fall. So if you happen to walk outside my room and you notice that there's a balcony, right, and you measure that, it happens to be 5.3 meters. Fancy that. Okay? So we will go out on Monday and you'll take an egg and you'll wrap it up in your container and then we'll drop them. And the goal is to do the same thing the airbag does, right? And the same thing the pillow does, and the same thing that the boxing gloves do, and the same thing that all of that is doing. Because for sure, that egg is going to experience a change in momentum. We want we want to minimize the force acting on the egg, right? So that it doesn't crack and break, okay? So your container must meet the following specifications. This is where it's maybe a little bit different from another one you've done. I'm going to give you 10 sheets of paper, okay? And I'll give you a roll of Scotch tape, okay? And that's what you get to do. That's what you get to use to build it, okay? The egg must not be added to in any way, so the tape can't stick onto the egg, okay? So you'll put an egg in, and then we'll drop it, and then hopefully it won't crack. The container must fall unrestrained. There must be no physical contact between you and the device, okay? And the container may not have a parachute. We have already done the air resistance lesson, right? This is not an air resistance lesson. This is a impulse momentum lesson, okay? So it's not going to catch it's going to fall. We can figure out how fast it's going to go when it hits the ground. Like, we can do that kinematics problem. But what I want is for you to then be able to successfully, support the egg. Once he's like, I got this, right? The egg must be put in just prior to the drop. So you're going to build this on Friday. You're not going to leave an egg in it over the weekend because we don't want that just in case the egg breaks, okay? So you'll design it on Friday, and then we'll test them on Monday. You do need to make sure that you clean up your mess if there happens to be one. You will have 2 tries for success. Does that make sense? So if it cracks the first time and you haven't, it hasn't completely destroyed your container, then you can absolutely try again. Does that make sense so far? Okay. It's pretty fun. So we'll build Friday and we'll test on Monday. On Monday, so how are we getting a grade for this? I'm not actually going to grade you on whether or not your container is successful. I am going to grade you on whether or not you understand why your container was successful or not. Okay, so on Monday, after we test, then I will give you a follow-up, a conclusion opportunity, and that will actually be that will be one of the pieces of evidence that go towards your standard of impulse momentum theorem. Yeah?
Can we build a little chamber for the egg?
You can do whatever you want as long as it fits into these things. Does that make sense?
Yep.
So you have to be able to open it up and add the egg right when we are going to test. And the egg can't be taped in there or anything. Yeah. Every person needs to have their own container. So you can, there's nothing to say that you can't you build one and your partner builds, or, your friend builds one, and you can you can exchange ideas, right? That's what engineering is all about. So that's totally fine with me. But we should have 4, 5, 6, 7, 8, 9, 10 containers to drop on that Monday. Okay, does that make sense?
Yeah.
Okay. In order to get you kind of thinking about what you will do and how you will go about this, I do have an interactive that I would like for you to work on before you actually start doing your big design process. Okay, there's a link on Canvas it's just like a little online simulator. Okay, it's not the same problem, but it's basically dropping an egg onto different materials and from different heights, and then some analysis to kind of look at that. So there are, I think, 9 questions and then a conclusion. This is not your homework for tonight. It's actually your homework for tomorrow. But I just wanted to give you this so that you had kind of some time to start thinking about ideas and come up with, some thoughts. Because again, on Friday, we will start building. Does that make sense to everybody? Questions right now before we move on to other things? Probably not a coincidence that they're copied on egg yolk colored paper. I don't know.
We did this freshman year, but with a little car.
Yeah, same thought process, different problem. Yes. All right, we have got time. Fantastic. Again, any questions on the egg drop before we move on? Okay, so you can just hold on to that. You can work on that whenever you want, but I would like it to be done by class day on Friday so that you're ready to go. Okay? All right. I got 2 rubber balls. They are about the same mass. They're about the same squishiness. I don't know. I'm gonna take a look at them. See if they trustworthy. You can hold them if you want. Yeah,
Yeah.
they're the same. They're the same, he says. All right, we're gonna try and drop them. I'm gonna drop them the same height. Let's see. Right here. It's going around the long way. Can I have you hold this out just so that I can make sure that I'm holding them up to the same height to start? Awesome, thank you. Oh, but now they can't see. Can you come stand around here? Otherwise, my eyes like, wait, I want to see the excitement. All right, here we go. Here we go. Ready? Let's see if I can drop at the same time. I don't trust myself, but here we go. 1, 2, 3, go.
That was cool.
Good. Again?
One of them completely.
Whoa, that one bounced off. But here it goes. Oh
Wait, are they the exact same? Is there something wrong with that one?
Wrong.
no! Something wrong. What wrong with which one?
I want to see it.
I mean,
Is it, can I see him? What kind of basketball does it
so the question is, which of the rubber balls experiences a greater force from the floor? So I want you to talk to your table mates. I want you to have a conversation
Wait.
and come up with an answer. Which
Can I
one?
bounce them?
Well, you can bounce one of them. The other one doesn't really bounce, but yes, you can.
can?
Thank you, Ryan. Yeah, it's right up there. Which of the rubber balls experiences a greater force from the floor? And why, really, is what I want, right? How do you know that that's the right answer? That's what I really care about.
It's right on the inside.
It's what's on the inside that counts.
Exactly.
There's the same mass, and it takes
Why doesn't
the
it
same time, and it's accelerating the same.
Can we see that? Yeah.
It's gotta be the same.
It's the same force.
Sorry, that was kind of mean. I apologize.
That's definitely close.
Yes, that's exactly like the gym.
Because
Something's inside.
if you think about
Well,
it, okay, so
they
you
have
got the 10
One of
pound
them's core.
So which of the rubber balls experiences a greater force? The one that doesn't bounce. I have a vote for doesn't bounce. Not bouncy.
How about that?
You vote for that one too?
Yes, me too.
I've got 3 votes.
I vote for the same amount of force.
Equal. Jordan, what are you voting for?
I don't want to vote.
Abstaining. Matt? Equal. Ryan? What do you think?
Not balanced.
Not bouncy. What do you guys think?
I'm kind of thinking equal.
Equal? Let's say. Equal? Equal. All right, let's find out. Let's figure this out.
Jordan, what do you got in mind? He wants
I don't want Jordan just voting on that.
He doesn't want to.
I don't want to be wrong.
He's insecure about being wrong. That's the problem. All right, so their masses are the same, yeah? So for the, let's do this kind of separate. So their masses are the same. Would you argue that when they both hit the ground, they are, because the not bouncy one still like pops up a little bit, right? Like there's a little. So how does the time compare for the bouncy one versus not bouncy one?
Bouncy one has more time.
You think
Yeah.
a lot more time or a little more time? What do you think? Let's watch. Can we do it one more time? I don't make it come up here. We'll just watch them. All right, so let's watch here. We'll do it on the table so you can see better a little bit. All right, so watch here. Which one is touching the table longer? Right at the very that moment. Here we go. 1, 2, 3, go. Which one touches the ground? Touches the table for longer? Right at the beginning.
Yeah, it looks like the same to me.
They both.
I think they look about the same. That's kind of what I was thinking too. I kind of feel like it's about the same. But I could be a little bit, I mean, like, appreciably, but like this one bounces really high, right? Or maybe it's this one, I don't know. But one of them bounces really high and the other one really doesn't. I think that the times are about the same.
Miss Carmen?
Yeah. I mean, I guess.
Can you no.
Let's just keep talking.
You change it up when it doesn't happen.
All right. How do their initial velocities right before they hit the table compare? This is kinematics, right? How fast is it going when it hits the ground? It's the same. So same, yeah? Which one has a higher final velocity? Which one has a bigger change in velocity? The bouncy ball does, doesn't it? Because it's going down really fast, and then it comes up almost as fast. Are you with me there? I think it's this one. Nope, it's not. I always get them wrong. This one, right? It goes down really fast, and then it comes back up pretty darn fast. So this one has a higher change in velocity. So which one has a higher force? Bouncy.
No, those are very.
Change in velocity. Bigger change in velocity, bigger change in momentum. Bigger change in momentum, bigger force.
Oh, darn.
Does that make sense?
Alright.
Yeah. It's just interesting. I'm not like, haha, right? I didn't give you this on a test. This is just a thinker question. Yeah? Just a little bit of a thinker. The answer is really, what is it, Jordan? What do you want to vote for now? Yeah. Convenient. I think it's bouncy. Like, sure you do. Of course you do now. All right. I'm going to throw this at you real quick because we haven't done this one yet, have we? Just real quick because we have a couple minutes. Just to get our brains really in there. It goes kind of with that last one. Go for it. Before and after snapshots of a car, its velocity are shown. All the cars have the same mass. Rank the magnitude of the change in momentum of the cars. Yes, and certainly talk to each other. Feel free. Have a conversation. Compare your answers. Are you writing in the book or something?
No,
Oh, okay.
it's just a spreadsheet.
Oh, gotcha. Did you come up with an answer? What was your answer? Did you say D or B?
B is greater than A, which is equal to D, which is greater than C.
What do you guys think?
Yeah.
What's the change in momentum for C? Zero?
Zero.
Change in momentum, or excuse me, the change in velocity, that's what I meant, because we don't know the mass, right? The change in momentum has to be zero also, isn't it? The other ones, we're just looking at change in velocity. Quick question for you. If these change in momenta happen over the same amount of time, which one experiences the greatest force? If those accelerations or those changes in velocity happened over the same amount of time, which one experiences the greatest force? B? Is that what you said? Woo! Which one is it? B.
B.
Yeah.
Wait, you said same
Same time. So FT equals M delta V. Yep.
The greatest one.
Yep. Same question that we've been doing all day. Yep.